Hello, welcome back. I'm Terry Collins. This is Lesson 1, Module 3. Green Chemistry focuses on inherent hazards. In this module, we'll talk about the concept of risk and how it's comprised of two key elements, hazard and exposure. We'll point out that green chemistry's focus is on the hazard component of risk. We'll consider how the concept of risk can help frame key sustainability issues. And we'll finish by discussing the point that green chemists have to be able to work, as with all other chemists, with hazardous substances safely. Well, this is the fundamental concept equation of green chemistry. Risk is a function of hazard times exposure. That means that the risk associated with each chemical is a function of its inherent hazard and the exposure of humans and the environment to that chemical. This simple relationship captures so much of what green chemistry is about. Green chemists focus on reducing the hazard function. The relationship represents a long-standing core idea on risk that was brought into green chemistry by Paul Anastas and John Warner in their 1998 book, Green Chemistry, Theory and Practice. Now, in order for us to see how the risk equation can help us evaluate sustainability problems, we will think about energy and compare the application of that equation to the different types of energy we use to run our civilization. Here, upon this beautiful piece of the earth, we find a human city. In the last 150 years, we've taken our human population, and concentrated it very largely in enormous cities around the world. These cities require a huge amount of energy to operate. Where does the energy come from? Primarily, our energy comes from fossil carbon sources. We mine coal and burn it in coal-fired plants to produce electricity. We extract oil from all over the planet in different locations, including from the deep sea. Particularly in the last decade in America, the natural gas industry has expanded greatly. This industry has learned how to access much more natural gas than historically, from deep underground through the process called hydrofracturing, and to bring the gas to the surface where it is burned primarily to generate electricity. Because we know how to build economies well around fossil carbon resources, our ongoing expansion, represented by the railway lines, in energy production globally remains associated with non-renewable oil, coal, and natural gas. Now let's think about how the risk equation applies to fossil carbon energy sources. There are many different types of risk associated with the individual industries. For example, we saw a very large hazard manifest itself in the oil leak into the Gulf of Mexico in 2010. Many people believe that the fracking chemicals associated with hydrofracturing to produce natural gas are extremely hazardous and represent severe pollution problems for air, water, and land. With carbon-based energy sources, there is also always an underlying problem in that carbon dioxide is released to the atmosphere as the fuel is burned, and carbon dioxide is a greenhouse gas. This gives rise to a risk equation that looks like the following. The hazard function associated with an individual carbon dioxide molecule with respect to global warming is minuscule, but the exposure function from all the carbon dioxide molecules released by burning fossil fuels is enormous and gives rise to a huge risk. The Intergovernmental Panel on Climate Control has told us that we are approaching CO2 levels in the atmosphere that portend serious changes to the global climate. When we began recording carbon dioxide concentrations in the atmosphere, the first full year was 1959, and the value was 315.98 parts per million. In the last 3 years, the numbers have risen as shown, such that in August 2010, we had 388.15 parts per million. Every single year now, the global CO2 concentration in the atmosphere is going up by more than 2 parts per million. This is a rate of increase that will put the atmospheric CO2 content at 450 parts per million in less than 30 years. 450 parts per million of CO2 in the atmosphere is a concentration that the IPCC has told us will give rise to a 50% likelihood of a catastrophic 2-degree increase in the average global temperature. Yet throughout the world, we are continuing to build carbon technologies in most of our countries. Now let's consider another place where we get a major source of energy, nuclear. With nuclear energy, the risk equation looks very different. Here, the inherent hazard associated with the radioisotopes of the nuclear industry is so large that the exposure function must be kept to 0. And in fact, because the half-lives of the radioisotopes involved are so long, the exposure function must be kept to 0 for hundreds of thousands of years. If you look at our two major sources of energy, carbon and nuclear, one can argue from evidence that we see around the world that we are really harming the planet in conspicuous ways. For example, we're warming the oceans, we're acidifying the oceans, we're polluting the oceans with heavy metals coming from coal-fired plants. Those metals are bioaccumulating up the ocean's food chain and are found now in high concentrations in our bigger predatorial fish that we like to eat. We are seeing an increase in the number of catastrophic floods around the world every year. We're seeing an increase in desertification. And we live always with the threat that there will be an accident or an event of some kind at one of our large nuclear plants, with the immense damage to health and the environment that such an event could produce. So it's clear that one can look at what's going on in the ecosphere around the planet and argue that our major approaches to energy are not working well for the sustainability of our civilization. Do we have alternative approaches? Well, fortunately, the Earth is bathed in sunlight. The Sun, a nuclear reactor 92 million miles from the Earth, produces so much energy that the Earth receives every hour more than enough energy to operate the human civilization for a year. We already have some outstanding technologies for capturing solar energy. For example, wind energy is based on solar because the wind is essentially generated by solar energy driving the atmosphere to move. We have photovoltaic technologies that are getting better and better every year and getting more cost-effective every year. With research, they'll undoubtedly get a great deal better. We have solar thermal technologies. And the Stirling engine-based technology, shown in the upper right-hand corner, is one of many examples. This one is up to 30% efficient on incident solar photon conversion to grid-ready AC current. And of course, plants convert solar photons into biomass, and biomass is potentially a major source of energy for operating our civilization out into the future. One of the really wonderful things about renewable energy technologies is the way the risk equation looks. The risk is small because the inputs and outputs of the nuclear reactor are 92 million miles away. Thus, we do not need to concern ourselves with the transformations of matter because these are extraterrestrial. Of course, it would be hard to imagine a riskless technology, and there are risks associated with the manufacturing, the siting, the operation, the disposal, and indeed the full life cycle of solar-based technologies. But overall, these look small when compared with huge releases of carbon dioxide or even tiny releases of radioactive nuclear isotopes. And so arguably, energy sustainability lies to the north on our particular map, toward the solar-based technologies of which we have discussed but a few. Thus, it is our responsibility to future humanity, no matter the magnitude of the barriers, to ensure that our civilization builds both literally and figuratively transportation lines towards a renewable, sustainable energy future. Health and environment must become integral components of the value proposition of technological progress if we're going to build a sustainable civilization. And this brings us right back to green chemistry. From a historical regulatory perspective, most action with hazardous chemicals has involved the exposure function. By lowering exposure, the risk is lowered. Exposure reduction usually takes the form of an intercepting technology, for example, a breathing apparatus, gloves, a leak-proof reactor, or more effective ventilation. Regulatory agencies end up setting maximum allowable exposures based on how serious they evaluate the hazard to be. The exposure limits can be adjusted as new information comes in, and allowed exposures have often been reduced with time. But it's important to keep in mind that this approach works only if the exposure controls don't fail. There are many recorded instances, from the ordinary to the spectacular, where exposure control failures have occurred. For example, in 2010, the Mexican Gulf oil leak crisis. In contrast, green chemists focus on the hazard function. By reducing or eliminating the inherent hazard through developing an alternative technology that is less hazardous, the risk is reduced. In principle, this is a more certain way of reducing risk, because this pathway is not subject to the potential for misuse or failure of an exposure-minimizing technology. Now, green chemistry is not about avoiding training in working with hazardous compounds. Being trained to deal safely with hazardous compounds is an important part of the technical training of a chemist. Hazardous chemicals often have unique properties that are important in chemical research, particularly in synthesis. Green chemistry's mission to reduce or eliminate hazardous substances does not override the need for advancing training in the safe use of hazardous chemicals. However, once a product is commercialized, it's obvious that it is in everyone's interest and appropriate ethically, environmentally, and economically that the hazards be as small as is possible. And it is with those chemicals that become widely distributed through the commercial products or processes where green chemistry's greatest powers lie for minimizing risk by reducing the hazard function.